Sometime in the summer of 2026, a rocket will launch from a small peninsula on the coast of New Zealand. It will carry a spacecraft roughly the size of a microwave oven. That spacecraft will coast through the void for 128 days before arriving at the most hostile destination humanity has ever dared to explore. And when it gets there, it will have exactly 5 minutes to answer one of the oldest questions ever asked. Are we alone? This is not a thought experiment. This is not science fiction. The probe is already being built. The instrument inside has been tested on an active volcano in Hawaii. The launch window opens in less than a year, and yet almost no one is talking about it. The Venus Lifefinder mission, the first private interplanetary spacecraft in history, is explicitly designed to search for signs of life in the clouds of Venus, not to look for water, not to study geology, but to hunt for the chemical fingerprints of biology on another world. The entire mission costs less than $10 million. That is roughly what a major Hollywood studio spends on catering for a single blockbuster film. And if it works, if this tiny probe plummeting through sulfuric acid clouds at 60 Gs manages to detect what it is looking for, it would be the most important scientific discovery in human history. So why is nobody paying attention? That is exactly what we are going to find out. Before we go any further, I need you to understand something about scale. The distance from Earth to Venus varies depending on where both planets are in their orbits. At their closest approach, just 40 million kilometers separate us, a journey of roughly 3 months at interplanetary speeds. At their farthest, when the Sun sits between us, that distance stretches to over 260 million kilometers. 40 million kilometers. That sounds like an incomprehensible number. Let me make it smaller. Light travels at approximately 300,000 kilometers per second. At closest approach, a radio signal from Venus reaches Earth in about 2 minutes and 13 seconds. That is less time than it takes to make coffee. The probe descending through Venusian clouds will be transmitting data that arrives on Earth faster than your pizza delivery notification. Mars, for comparison, is never closer than 54 million kilometers to Earth, usually much farther. The record closest approach was in 2003, and even then, Mars remained distant enough that light took over 3 minutes to cross the gap. Venus is our closest planetary neighbor. It is literally easier to reach than Mars. The launch windows are more frequent. The travel time is shorter. The communication delay is briefer. And yet Mars has received dozens of missions, while Venus has been largely ignored for 4 decades. This is one of the strangest decisions in the history of space exploration, and the Venus Lifefinder mission, in its own small way, is an attempt to correct it. To understand why we are sending a probe to Venus, you first have to understand what Venus really is, and more importantly, what it used to be. Right now, Venus is a nightmare. The surface temperature averages 465 degrees Celsius. That is hot enough to melt lead. It is hot enough to soften aluminum. It is hotter than the hottest setting on most industrial ovens. And that temperature is constant everywhere on the planet. Dayside, nightside, equator, poles. Venus does not cool down. Ever. The atmosphere is 92 times denser than Earth's. Standing on the surface of Venus would feel like being a kilometer underwater in our oceans. The pressure alone would crush any standard spacecraft in minutes. Add in the heat, and you begin to understand While the Soviet Union's Venera probes, the only vehicles ever to land on Venus and transmit data, survived for a maximum of 2 hours before going silent forever. The clouds are composed primarily of sulfuric acid, not water, not even carbon dioxide, actual concentrated sulfuric acid that would dissolve most materials on contact. The winds in the upper atmosphere blow at 360 kilometers per hour, circling the entire planet in just 4 Earth days, even though Venus itself takes 243 Earth days to complete a single rotation. This is called superrotation, and after decades of study, we still do not fully understand how it works. Venus is, by virtually every measurable standard, the most inhospitable place we have ever tried to explore. And yet, something very strange happened in 2020 that changed everything. But before we get to 2020, I need to take you back further, much further. 4.5 billion years ago, when the solar system was young and chaotic, 2 planets formed from the same primordial cloud of gas and dust, orbiting at similar distances from a newly ignited star. They were nearly identical in size, composition, and mass. They received comparable amounts of solar energy. They condensed from the same raw materials. They were twins. One of those twins became Earth. The other became Venus. For the first billion years or so, the differences were minimal. Both planets had atmospheres. Both had volcanic activity. Both likely had oceans of liquid water. Computer models suggest that ancient Venus maintained stable surface temperatures between roughly 20 and 50 degrees Celsius, warmer than Earth today, but perfectly hospitable for life. How long did this last? Estimates vary. Some models suggest water persisted on Venus for as little as 600 million years. Others push the timeline to 2 or even 3 billion years. The most recent studies from NASA's Goddard Institute for Space Studies suggest habitable conditions may have lasted until just 700 million years ago, shockingly recent in geological terms. To put that in perspective, life on Earth is approximately 4 billion years old. If Venus had comparable conditions for even a fraction of that time, there was ample opportunity for something to arise. And if it did arise, it had hundreds of millions of years to evolve before catastrophe struck. Because catastrophe did strike. Something happened to Venus that transformed it from Earth's twin into Earth's nightmare. The leading hypothesis involves volcanism. Around 700 million years ago, Venus appears to have undergone a massive resurfacing event. Volcanic eruptions so extensive that they buried 80% of the planet's surface in fresh lava. This event, or series of events, released enormous quantities of carbon dioxide that had been locked in crustal rocks. Carbon dioxide is a greenhouse gas. It traps heat. On Earth, we worry about atmospheric carbon dioxide levels reaching 450 parts per million. Venus's atmosphere is 96% carbon dioxide. The effect was catastrophic and self-reinforcing. More carbon dioxide meant higher temperatures. Higher temperatures meant more water evaporated into the atmosphere. Water vapor is also a greenhouse gas, so temperatures rose further. Eventually, the oceans boiled away entirely. Without liquid water to sequester carbon dioxide through weathering and plate tectonics, the carbon dioxide just kept accumulating. This is what scientists call a runaway greenhouse effect, and it transformed Venus from a potentially habitable world into the hellscape we observe today. Understanding this history is crucial because it frames the question we are really asking. We are not asking whether life could arise on modern Venus's surface. Obviously, it cannot. We are asking whether life that arose on ancient Venus could have adapted to survive in the only remaining habitat, the clouds. In September of 2020, an international team led by astronomer Jane Greaves at Cardiff University made an announcement that sent shockwaves through the scientific community. Using two of the most powerful radio telescopes on Earth, the James Clerk Maxwell Telescope in Hawaii and the ALMA Array in Chile, they had detected something that should not exist in the Venusian atmosphere: phosphine. Phosphine is a molecule made of one phosphorus atom and 3 hydrogen atoms. On Earth, there are exactly 2 ways to produce it. You can make it artificially in a laboratory using industrial chemistry, or it can be produced by certain anaerobic bacteria, microorganisms that live without oxygen in environments like swamps, sewers, and the guts of animals. That is it. Those are the only known sources. On a rocky planet like Venus, with its oxygen-rich upper atmosphere and intense solar radiation, phosphine should not exist. Any molecule of it that appeared would be destroyed almost immediately by the sun's ultraviolet rays. And yet the team was detecting it at concentrations of around 20 parts per billion, a tiny amount in absolute terms, but impossibly high given what we know about Venusian chemistry. Greaves and her colleagues spent over a year trying to explain the finding through conventional means. Volcanic activity, the amount of sulfur released, would have to be orders of magnitude higher than anything we have evidence for. Lightning strikes, the energy levels required are astronomical. Photochemistry in the upper atmosphere, they ran the models. Nothing worked. The team published their results in the journal Nature Astronomy with a conclusion that was simultaneously cautious and explosive. They could not identify any abiotic source sufficient to explain the phosphine concentration. The implication was clear, even if the authors never said it directly. Life remained on the table. The implications of the phosphine detection went beyond the molecule itself. If phosphine truly exists in Venus's atmosphere at the concentrations reported, something must be constantly producing it. The molecule has a very short lifetime in the Venusian environment. Solar radiation and chemical reactions with other atmospheric compounds would destroy it within years, possibly within months. A sustained concentration of 20 parts per billion requires a continuous source. On Earth, we understand phosphine production fairly well. The industrial process involves combining phosphorus with hydrogen under high temperature and pressure, conditions that do not exist naturally on Venus. The biological process involves specialized enzymes in anaerobic bacteria that reduce phosphate minerals to phosphine as part of their metabolism. Neither process seemed applicable to Venus. The planet has no industrial chemistry. And if the biological explanation required bacteria similar to Earth's, how could such organisms survive in concentrated sulfuric acid? This is where the science becomes genuinely interesting. The phosphine team did not simply announce their detection and claim aliens. They spent over a year systematically eliminating alternative hypotheses. Their paper and the extensive supplementary material accompanying it represents one of the most thorough attempts in astrobiology to rule out non-biological explanations. They considered volcanic outgassing. Venus has active volcanoes. Magellan radar data and recent observations suggest ongoing volcanic activity, possibly including eruptions within the past few decades. Could volcanic phosphorus compounds be converted to phosphine in the atmosphere? The team calculated the required volcanic output and found it would need to be hundreds of times greater than anything observed on Earth. releasing quantities of sulfur that would alter the entire atmospheric chemistry in ways we do not observe. They considered lightning. The Venusian atmosphere has electrical activity. Could lightning strikes provide enough energy to synthesize phosphine from atmospheric components? The calculations suggested the energy requirements were orders of magnitude beyond what Venus's lightning could provide. They considered meteoritic delivery. Small bodies constantly bombard the inner solar system, and some contain phosphorus compounds. Could meteors be seeding Venus's atmosphere with phosphine? The flux would need to be impossibly high, and the phosphine would be destroyed faster than it could accumulate. They considered photochemistry, reactions driven by sunlight that might produce phosphine as a byproduct. They modeled hundreds of potential reaction pathways. None produced phosphine in detectable quantities. At the end of this systematic elimination, they were left with a mystery. Something was producing phosphine on Venus, and that something did not match any known abiotic process. The team was careful never to claim they had found life. What they claimed precisely was that they had found a molecule whose presence demanded explanation, and that biological production could not be ruled out. In science, this is how you announce an extraordinary possibility without overstepping your evidence. The phosphine announcement was not received gently. Within weeks, papers appeared challenging every aspect of the detection. Other researchers reanalyzed the ALMA data and claimed the signal was actually from sulfur dioxide, a molecule that is abundant in Venus's atmosphere. Some argued the statistical analysis was flawed. Others questioned whether the telescopes were calibrated properly for observing such a bright target. Greaves and her team responded to each criticism. They acknowledged errors in their initial data processing, which reduced the estimated phosphine concentration but did not eliminate it, and they ran new analyses with different methodologies. The signal persisted. Then, more detections came. Using the NASA SOFIA Airborne Observatory, using the JCMT again with upgraded instruments, using archived data from the Pioneer Venus mission that landed in 1978. Each time, evidence of phosphine appeared. As of today, there have been 5 independent detections spanning nearly half a century of data. The scientific debate continues, with some teams reporting upper limits inconsistent with the claimed detections, and others finding confirmation. Jane Greaves summarized the situation at a recent astronomy conference. There appears to be some steady source of the gas, something actively producing phosphine, faster than the Venusian atmosphere can destroy it. What that source might be remains completely unknown. But here is the critical point. The only way to resolve this controversy is to go there and look. Enter Sara Seager. If you want to understand the Venus Life Finder mission, you have to understand the person who made it happen. Sara Seager is not a fringe scientist chasing aliens. She is one of the most accomplished astrophysicists of her generation. Born in Toronto in 1971, Seager received her PhD from Harvard in 1999, the same year the first exoplanet atmosphere was detected, a discovery her doctoral thesis had helped predict. She pioneered the theoretical framework for identifying biosignature gases on distant worlds. She developed a modified version of the famous Drake equation specifically for detecting life through atmospheric chemistry. She was the deputy science director of NASA's TESS mission, which has discovered thousands of exoplanets. She is a MacArthur Fellow, a member of the National Academy of Sciences, an officer of the Order of Canada, and has an asteroid named after her. When Phosphine was announced in 2020, Seager was part of the team that found it. She had been working on Phosphine as a potential biosignature for years before anyone thought to look for it on Venus. Her name appears on the original Nature Astronomy paper, and when the scientific community erupted in controversy, she did something nobody expected. She decided to build a spacecraft. The path from astronomical controversy to actual hardware began, of all places, in a Zoom meeting. In the months following the Phosphine announcement, Seager began organizing planning sessions for potential Venus missions. Scientists from around the world joined these virtual gatherings: atmospheric chemists, planetary geologists, astrobiology specialists, all brainstorming what instruments might help resolve the Phosphine debate. One of these meetings included an unexpected participant, someone from Rocket Lab, a relatively small aerospace company based in California that had built its reputation launching small satellites on its Electron rocket. That company's founder and CEO, Peter Beck, had been obsessed with Venus for years. A self-taught rocket engineer from New Zealand, Beck had started Rocket Lab with a vision of making space more accessible. But his personal dream went far beyond commercial launches. According to Beck, the earliest memory he has is standing outside with his father, looking up at the night sky. His father pointed to the stars and told him that every one of them might have a planet, and there might be someone on one of those planets looking back at them. That moment defined his life. After the Zoom call, Rocket Lab reached out to Seager's team with an offer that sounded almost too simple. They had the rocket. They had the spacecraft bus. They could get to Venus relatively cheaply. Did the scientists have a single focused instrument that could fit? The Venus Lifefinder mission was born. I need to pause here and explain why this moment matters in the history of space exploration. For 60 years, interplanetary missions have been the exclusive domain of national space agencies: NASA, Roscosmos, ESA, JAXA, CNSA. These organizations have the budgets, the infrastructure, and the institutional knowledge to send spacecraft to other worlds. A typical planetary mission costs between $500 million and $2 billion, requires a decade or more of development, and employs thousands of engineers and scientists. This model has produced extraordinary science: Voyager, Cassini, Mars rovers, New Horizons. The legacy of government-funded planetary exploration includes some of humanity's greatest achievements, but it has also created a bottleneck. NASA can only select 2 or 3 new missions per decade. Proposals that do not make the cut wait years for another opportunity. Revolutionary ideas compete against safe, well-understood concepts in a process that inevitably favors incremental progress over bold exploration. The Venus Lifefinder represents something genuinely new, a private interplanetary mission developed outside the traditional institutional framework, not funded by NASA, not selected through a competitive peer review process, not bound by government procurement regulations or congressional appropriation cycles. Instead, a small team, fewer than 30 people, working with existing commercial hardware, funded by philanthropic donations and corporate investment, designing a mission specifically to answer one focused question. If this model works, the implications extend far beyond Venus. It would demonstrate that interplanetary exploration can be democratized, that organizations outside the traditional space establishment can contribute meaningfully to humanity's understanding of the solar system. Peter Beck understood this from the beginning. At the very least, he said in an interview, I think it's a needle mover, even for just a private mission, to try and go do something interplanetary. That sends a message to the rest of the world that, hey look, we can do these things privately. The philosophy behind Venus Life Finder is almost aggressively minimalist. Most planetary missions cost hundreds of millions of dollars, require decades of development, and carry suites of instruments designed to answer multiple scientific questions. NASA's upcoming DAVINCI mission to Venus, for example, will carry 4 major instruments on its descent probe alone, with a price tag around $500 million, and a launch date no earlier than 2031. Venus Life Finder costs less than $10 million. It carries 1 instrument, and its entire science phase lasts approximately 5 minutes. This is not a limitation, it is a strategy. The probe is tiny, a cone-shaped capsule, roughly 40 centimeters across, weighing only 17 kilograms. Inside that cone, protected by a spherical titanium pressure vessel and surrounded by high-temperature insulation, sits the autofluorescence nephelometer. The AFN is the heart of the mission, built by Droplet Measurement Technologies in collaboration with scientists from MIT, Georgia Tech, and multiple other institutions. It works on a principle that is elegant in its simplicity. The instrument fires a 440 nanometer blue laser beam out through a fused silica window into the Venusian clouds. As the probe plummets through the atmosphere, cloud particles pass through this laser beam. Some of the light scatters in measurable patterns that reveal the particle's size, shape, and optical properties. But the really clever part is what happens if those particles contain organic molecules. Many organic compounds fluoresce when struck with certain wavelengths of light. They absorb the incoming photons and re-emit light at a slightly different wavelength, a phenomenon you have seen if you have ever been in a room with blacklight posters or examined certain banknotes under ultraviolet lamps. The AFN is specifically tuned to detect this fluorescent signal. If the cloud particles are pure sulfuric acid and nothing else, the scattered light will show a specific signature. If those particles contain organic materials, carbon-based molecules, with the ring structures common to biology, they will glow. That glow would be, in the words of the mission scientists, a smoking gun. The instrument has already been tested under conditions approximating those it will face on Venus. In May of 2005, a multidisciplinary research team led by Georgia Tech brought the AFN prototype to the Kilauea volcano in Hawaii. The volcano was actively erupting at the time, producing sulfur-rich volcanic gases that share some chemical similarities with the Venusian atmosphere. The team flew the instrument through the volcanic plume, collecting measurements that would serve as a baseline for comparison with whatever the probe detects at Venus. The Hawaii campaign served multiple purposes. It validated the instrument's ability to distinguish between organic and inorganic particles in a sulfur-rich environment. It tested the data processing algorithms under field conditions, and it provided crucial calibration data that will help researchers interpret the Venus measurements. Christopher Carr, an aerospace engineer at Georgia Tech and one of the mission's co-investigators, described the fluorescence detection capability as a potential smoking gun for organic materials. The logic is straightforward. Pure sulfuric acid droplets should not fluoresce. If the instrument detects fluorescence, something besides sulfuric acid is present in those particles. The technical specifications of the AFN are carefully tuned to maximize the chance of detection. The 440 nanometer laser wavelength was selected because it efficiently excites fluorescence in many organic compounds are being easily transmitted through the probe's fused silica window. The detection wavelength range, 470 to 520 nanometers, corresponds to the emission spectrum expected from organic ring structures. This is not general-purpose instrumentation. This is a scalpel designed to answer one specific question. The mission profile itself reads like a controlled exercise in calculated risk. The probe will launch sometime in the summer of 26 aboard Rocket Lab's larger Neutron rocket, a vehicle that has not yet made its first flight as of this writing. The spacecraft will consist of two parts: the Photon Explorer cruise stage, an interplanetary version of Rocket Lab's proven satellite bus, and the atmospheric probe containing the AFN. After launch, the spacecraft will spiral outward from Earth through a series of carefully timed engine burns, eventually using the Moon's gravity as a slingshot to escape the Earth-Moon system entirely. The journey to Venus will take approximately 128 days. 30 minutes before atmospheric entry, the Photon stage will release the probe and perform a divert maneuver to avoid following it into the clouds. The probe will enter on Venus's night side, deliberately chosen to minimize background light that could interfere with the fluorescence measurements, and immediately begin experiencing forces that would destroy most spacecraft. Peak deceleration will hit 60 Gs. The probe has no parachute. It will simply fall, using the dense Venusian atmosphere itself to slow its descent. This is exactly the same approach used by NASA's Deep Space 2 probes that crashed into Mars in 1999, and the Venus Lifefinder probe's outer shell is directly based on that design. The science window opens at an altitude of approximately 65 kilometers, the top of the Venusian cloud layer, and closes at 45 kilometers, where temperatures and pressures exceed what the probe can survive. That gives approximately 5 minutes of data collection as the probe falls at terminal velocity through the most intriguing region of Venus's atmosphere. Throughout this descent, the AFN will be firing its laser, measuring scattered light, and watching for fluorescence. The probe's S-band transmitter will relay everything directly to Earth in real time, bypassing the Photon cruise stage entirely. The data rate is painfully slow, only 125 bytes per second, but the team has developed neural network algorithms to compress the most critical information into that tiny bandwidth. Then, after roughly 30 minutes from atmospheric entry, the signal will die. The probe will continue falling, heating up, being crushed by ever-increasing pressure until nothing remains but debris scattered across the Venusian surface. And that will be the end. Unless, of course, the probe detects something first. Here is where I need to tell you about Venus's clouds. The surface of Venus is undeniably lethal. No known life could survive there. But 50 kilometers above that surface, conditions are remarkably different. The temperature at this altitude ranges from about 20 to 50 degrees Celsius, room temperature, roughly. The atmospheric pressure is approximately 1 Earth atmosphere, exactly what you are experiencing right now. The gravity is about 90% of Earth's. If you were floating in a balloon at this altitude, on Venus, wearing only an oxygen mask and protective clothing against the acid, you would be more comfortable than anywhere else in the solar system outside of Earth. This is not a new observation. In 1967, Carl Sagan and biophysicist Harold Morowitz published a paper in the journal Nature titled simply Life in the Clouds of Venus. Even then, half a century before the Phosphine controversy, they recognized that while the Venusian surface was hellish, the clouds might be another story entirely. Their hypothesis was speculative, but grounded in basic physics. What if life had evolved on Venus when the planet was more Earth-like, billions of years ago, and then adapted to survive in the clouds as the surface became uninhabitable? We now know this timeline is plausible. Computer models from NASA's Goddard Institute for Space Studies suggest Venus may have had shallow liquid water oceans and surface temperatures comparable to Earth for up to 2 billion years. That is far longer than life needed to evolve on our planet. If life arose on ancient Venus as it did on ancient Earth, it had ample time to adapt as conditions changed. The key question is whether anything could survive in those clouds today. The Venusian cloud layer presents challenges that would destroy most Earth life instantly. The droplets are concentrated sulfuric acid, not dilute acid like car battery fluid, but nearly pure sulfuric acid. The water activity is vanishingly low, meaning any water that exists is essentially locked up in the acid and unavailable for biological processes. Ultraviolet radiation from the sun is intense at cloud-top altitudes. And yet, on Earth, we have discovered organisms that defy nearly every assumption about the limits of life. Acidophiles thrive in environments with pH levels near zero, inside volcanic hot springs, acid mine drainage, even the concentrated sulfuric acid pools found in some geothermal regions. Thermophiles survive at temperatures exceeding 120 degrees Celsius, far hotter than Venus's habitable cloud zone. Organisms at the bottom of the Mariana Trench withstand pressures over 1,000 times greater than what Venus's clouds impose. The key insight from decades of extremophile research is not that life tolerates extremes, it is that life exploits them. Organisms do not merely survive in harsh environments, they evolve to use those environments' unique chemistry for their metabolism. Sulfur oxidizing bacteria in deep sea vents derive energy from hydrogen sulfide. Acidophilic archaea in volcanic hot springs use sulfur cycling to produce sulfuric acid as a metabolic byproduct. Sulfuric acid, the very substance that makes Venus's clouds so apparently deadly. Sara Seager and her colleague Janusz Petkowski have conducted laboratory experiments showing that certain organic molecules, informational polymers similar in function to DNA, remain stable when exposed to concentrated sulfuric acid. The assumption that concentrated acid destroys all biochemistry turns out to be incorrect. Some molecular structures survive. Some might even thrive. This does not prove life exists on Venus. What it proves is that the absence of life cannot be assumed. There is another mystery in Venus's clouds that the Phosphine discovery overshadowed, but which may be equally significant. When you look at Venus in ultraviolet light, the planet is not a uniform sphere. Instead, you see dark patches, regions that absorb UV radiation far more strongly than the surrounding clouds. These patches shift and change over time, creating patterns that sometimes look almost like weather systems, sometimes like nothing we can explain. We have known about this unknown UV absorber since the 1920s, when astronomer Frank Ross first photographed Venus through ultraviolet filters. For nearly a century, scientists have proposed various explanations: iron chloride particles, allotropes of sulfur, complex photochemical products. None of these explanations fully fit the observations. In 1963, Carl Sagan proposed something more radical. What if the UV absorber was biological? What if the dark patches were essentially algae blooms in the Venusian sky, colonies of microorganisms absorbing sunlight for energy? exactly as cyanobacteria do in Earth's oceans. Recent analysis has added an unsettling detail. The particles making up the dark patches are approximately the same size as certain bacteria found on Earth. This proves nothing. Plenty of non-biological particles fall into that size range, but it adds another entry to the growing list of Venusian anomalies that would make sense if life were present. The Venus Life Finder probe cannot directly identify what causes the UV absorption, but if those particles contain organic molecules, the AFN will detect their fluorescence. We will finally have data from inside the clouds rather than spectra gathered from Earth-based telescopes 100 million kilometers away. Now, I need to address the elephant in the room. Why Venus? Why not Mars? Mars has dominated astrobiology for decades. The rovers, the orbiters, the planned sample return missions, the endless speculation about fossil microbes in ancient lake beds. Mars receives 10 times the research funding, 100 times the media attention, and practically all the cultural mindshare when it comes to extraterrestrial life. Here is the uncomfortable truth. Mars is, in many ways, less promising than Venus. The Martian surface today is frozen, irradiated, and essentially sterile. If life existed there, it almost certainly went extinct billions of years ago, when Mars lost its atmosphere and its water evaporated into space. The best we can hope to find are fossils, chemical traces of biology that ceased long before humanity existed. Venus's clouds, by contrast, are not fossils. They are active environments, right now, today, with the temperature and pressure conditions that terrestrial life finds comfortable. If something lives there, it is alive at this moment, not preserved, not ancient, currently metabolizing, currently reproducing. The history of Mars versus Venus exploration reveals a fascinating divergence in priorities. In the early space age, Venus received more attention than Mars. The Soviet Union sent probe after probe to our closest planetary neighbor, achieving remarkable firsts that stood for decades. The United States, while less focused on Venus, still contributed important missions. Mariner 2 in 1962, the first successful planetary flyby. Mariner 5 in 1967. Mariner 10 in 1973. And the Pioneer Venus missions in 1978. Then something changed. Starting in the 1980s and accelerating through the 1990s and 2000s, Mars became the overwhelming focus of planetary exploration. NASA sent mission after mission. Vikings, Mars Global Surveyor, Mars Pathfinder, Mars Odyssey, Spirit, Opportunity, Phoenix, Curiosity, Insight, Perseverance. The European Space Agency contributed Mars Express. India launched Mangalyaan. China sent Tianwen-1. Meanwhile, Venus received almost nothing. After the Soviet Venera program ended in 1984, only 3 dedicated Venus missions launched over the next 4 decades. NASA's Magellan Radar Mapper in 1989, ESA's Venus Express Orbiter in 2005, and Japan's Akatsuki Climate Orbiter in 2010. None of these carried instruments designed to investigate the potential habitability of the clouds. The reasons for this divergence are complex. Mars has a thin atmosphere that makes landing easier. Mars has a solid surface that rovers can explore. Mars has geological features that look familiar: river valleys, lake beds, polar ice caps, while Venus is shrouded in clouds that hide its surface from visible light observation. Mars captured the public imagination through science fiction narratives that Venus never quite matched. But the scientific rationale is harder to justify. If the goal is to find evidence of current life that exists now, not life that existed billions of years ago, Venus may actually be the better target. The clouds are potentially habitable today, in the present tense, in a way that the frozen Martian surface simply is not. The Venus Life Finder represents a correction to this imbalance, not an abandonment of Mars exploration, but a recognition that our closest planetary neighbor deserves attention it has been denied for far too long. The detection of living extraterrestrial organisms would be categorically different from finding chemical traces of dead ones. It would mean life is not merely possible elsewhere, it is actual, ongoing, present tense. That distinction matters more than any other factor in the search for life beyond Earth. Peter Beck, the CEO of Rocket Lab, put it simply in an interview: "I think there's a real chance of actually finding a meaningful existence of life in the clouds of Venus. It's not a super high chance, but it's possible. And if it's possible, it must be done." The case for Venusian clouds as a potential habitat grows stronger the more carefully you examine the data. Start with temperature. The habitable cloud zone between approximately 48 and 60 kilometers altitude maintains temperatures ranging from roughly 0 to 60 degrees Celsius. This is not just tolerable by human standards, it is comfortable. You would need a jacket at the higher altitudes, but at 50 kilometers, a light sweater would suffice. Now consider pressure. At the same altitude range, atmospheric pressure varies from approximately half an Earth atmosphere to about 1 Earth atmosphere. Again, this is not extreme. Humans live at similar pressures in high-altitude cities like La Paz and Lhasa. The atmospheric composition would kill you 96% carbon dioxide with sulfuric acid droplets. But the physical environment is remarkably Earth-like. Gravity on Venus is 90% of Earth's, close enough that biological processes adapted to Earth gravity would function normally. Sunlight filtering through the clouds provides ample energy for photosynthesis, if any organisms present could capture it. The remaining challenge is the chemistry. Sulfuric acid droplets and minimal water availability seem to preclude life as we know it, but this assumption deserves scrutiny. First, the acid. Sulfuric acid is undeniably corrosive to most organic materials, but most is not all. Earth hosts acidophilic organisms that thrive at pH levels near 0, the acidity of concentrated battery acid. The Archaeon Picrophilus torridus holds the current record, growing optimally at pH 0.7 and surviving exposure to pH values below 0. These are not marginal survivors. They are highly specialized organisms that require extreme acidity for their metabolism. More intriguingly, sulfur-oxidizing bacteria on Earth produce sulfuric acid as a metabolic byproduct. They take in sulfur compounds and excrete sulfuric acid. The very substance that makes Venus's clouds seem deadly is, on Earth, a waste product of microbial metabolism. Second, the water. Venus's clouds are extremely dry by Earth standards. The water activity, a measure of available water for biological processes, is far below anything terrestrial life has demonstrated tolerance for. This seems like a fatal objection, but Sara Seager's laboratory has demonstrated that some organic molecules remain stable in concentrated sulfuric acid. The acid itself might serve as a solvent for certain biochemical reactions, replacing water's role in terrestrial biochemistry. We have no examples of acid-based life on Earth, but we also have no definitive theoretical prohibition against it. The point is not that Venusian life is likely. The point is that we cannot rule it out through theoretical arguments alone. Every objection based on Earth-centric assumptions runs into the same problem. We are extrapolating from a single example. The Soviet Union understood something about Venus that the rest of the world forgot. Between 1961 and 1984, the USSR launched over 30 missions to Venus as part of its Venera program. This was not casual exploration. It was one of the most sustained and ambitious planetary science campaigns in history. The early missions failed, often catastrophically. The first 7 attempts between 1961 and 1964 ended with launch failures or communications losses. Venera 1 went silent 7 days after launch. Venera 2 overheated during its Venus flyby and transmitted nothing. But the Soviets learned, they adapted, and they eventually achieved a series of firsts that no other nation has matched. Venera 4 in 1967, first successful atmospheric probe of another planet, transmitting data as it descended until the pressure crushed it. Venera 7 in 1970, first soft landing on another planet, surviving on the surface for 23 minutes. Venera 9 in 1975, first photographs from the surface of another planet, grainy, orange-tinged images showing angular rocks scattered across a barren volcanic plain. Venera 13 in 1982, first color photographs from Venus, first audio recording from another planet's surface, first soil analysis. The probe lasted 127 minutes before falling silent. Each of these missions was a marvel of engineering against impossible odds. The probes were essentially armored pressure vessels designed to withstand temperatures that would melt most electronics and pressures that would collapse most structures. They had hours to complete their science before the planet destroyed them. And then, in 1984, the Soviet program ended. Funding dried up, priorities shifted. The fall of the USSR scattered the expertise that had been painstakingly accumulated over 2 decades. Since then, there have been exactly 0 landers or atmospheric probes sent to Venus by any nation. The Venus Lifefinder mission, launching roughly 40 years after Venera, will be the first return. The gap between the last Soviet missions and Venus Lifefinder is not merely a historical curiosity. It represents an enormous missed opportunity that we are only now beginning to address. Consider what the Venera probes achieved with 1970s and 1980s technology. Venera 13, the most successful lander, carried a suite of instruments that would be considered sophisticated even today. X-ray fluorescent spectrometers for soil analysis, panoramic cameras, a drill and sample acquisition system, microphones to record the Venusian soundscape. All of this was packed into a pressure vessel that survived 2 hours on a surface hot enough to melt tin. The photographs from Venera 13 remain, to this day, the highest quality images ever taken on the surface of Venus. They show a landscape of flat volcanic rocks, fractured basalt plates, and fine-grained soil, a world that looks surprisingly Earth-like despite its lethal conditions. The orange tint comes from the filtering effect of Venus's thick atmosphere, which scatters blue and green light while allowing red and orange wavelengths to reach the surface. The audio recordings captured the sound of Venusian wind, a low, consistent rushing noise with occasional variations as gusts passed the lander. No other mission has ever recorded the ambient sound of another planet's atmosphere. And then it all stopped. The Soviet space program collapsed with the Soviet Union itself. Russia's space agency, Roscosmos, inherited the Venera legacy but lacked the funding and political will to continue it. The United States, meanwhile, had never prioritized Venus the way it prioritized Mars. The result is a 4-decade gap in our understanding of our closest planetary neighbor. We have better surface maps of Mars, a planet that is, at best, 50% farther away than we do of Venus. We have sent more than 50 missions to Mars since the last Venera landing. We have sent 0 landers or atmospheric probes to Venus. The Venus Life Finder does not carry instruments comparable to the Venera probes. It cannot land. It cannot drill. It cannot photograph the surface. But it can do something the Venera probes never attempted: directly analyze cloud particles in the potentially habitable altitude range, looking for chemistry that the Soviets never thought to investigate. In some ways, the timing is perfect. We now know to ask questions that scientists in the 1980s could not have formulated. The phosphine controversy has focused attention on the clouds as a potential habitat. Advances in extremophile research have expanded our understanding of life's limits. The Venus Life Finder is not just a return to Venus, it is a return with better questions. NASA is planning to return to Venus as well, but the timeline is sobering. In June 2022, the agency announced that 2 Venus missions, DAVINCI and Veritas, had been selected as part of its Discovery program. Both were originally scheduled to launch before 2030. Both have since been delayed due to budget constraints and technical challenges. Current estimates place DAVINCI's launch no earlier than 2031. DAVINCI is the direct comparison to Venus Life Finder. It will send an atmospheric descent probe to Venus, carrying multiple instruments designed to measure atmospheric composition down to the surface. It is a far more capable mission in every technical dimension. Its instruments will directly detect noble gases, trace chemicals, and isotope ratios that can reveal Venus's entire atmospheric history. But it costs $500 million. It requires a decade of development. It represents the full weight of NASA's institutional approach to planetary science: rigorous, methodical, and extremely slow. The Venus Life Finder costs less than 2% of DAVINCI's budget. It will launch 5 years earlier. Its single instrument asks a narrow question, but that question happens to be the most important one we can ask about any world. Is anyone home? The 2 missions are not competitors. They are complements. If Venus Life Finder detects organic molecules in the clouds, DAVINCI will arrive with the tools to characterize them in exquisite detail. If Venus Life Finder detects nothing, that negative result will still constrain the possibilities and help focus DAVINCI's investigation. But there is another possibility, one that makes the timeline truly urgent. What if Venus Life Finder detects something unmistakable? What if that tiny probe, with its single instrument and its 5-minute window, returns a signal that can only mean one thing? In that case, waiting until 2030, one would feel like an eternity. The broader context matters here. We are living through what might be called a golden age of astrobiology. For the first time in human history, we have the technological capability to answer the question of whether life exists beyond Earth. The James Webb Space Telescope can analyze the atmospheres of exoplanets for biosignature gases. Missions to Europa and Enceladus, moons with subsurface oceans, are in development. Mars sample return, despite its cost and complexity, remains a priority. Venus represents the most accessible target in this search. It is closer than any other potentially habitable world. The transit time is measured in months, not years. The communication delay is measured in minutes, not hours. If life exists anywhere in our solar system, beyond Earth, Venus's clouds are among the most plausible locations, and certainly the easiest to reach. The Venus Life Finder is explicitly designed as the first mission in a sequence. Sara Seager and her team have outlined a roadmap called the Morning Star missions to Venus, consisting of progressively more sophisticated probes. The current mission searches for organic molecules. A follow-up mission might characterize those molecules in greater detail. A balloon mission might hover in the clouds for extended observation. Eventually, a sample return mission might bring Venusian cloud material back to Earth for laboratory analysis. Each step builds on the previous one. Each detection narrows the possibilities and refines the next investigation. This is how systematic science proceeds, not through single dramatic discoveries, but through accumulating evidence that points increasingly toward or away from particular hypotheses. The Venus Life Finder is the first step. If it finds nothing, the Morning Star program might be scaled back or redirected. If it finds something, even something ambiguous, it justifies the next mission, and the next, until we have an answer. Each step would narrow the possibilities. Each detection would constrain the hypotheses. And somewhere along that path, perhaps soon, perhaps decades away, we might reach the point where no abiotic explanation remains. That would be the moment. The discovery that changes everything. Here is something people do not often consider about the search for extraterrestrial life. We do not actually know what we are looking for. All life on Earth, every organism ever studied, from single-celled bacteria to blue whales, shares common biochemistry. We use DNA to store genetic information. We use proteins to catalyze chemical reactions. We use lipid membranes to separate inside from outside. We use water as a solvent for all our metabolic processes. But this is a sample size of 1. We have no idea whether these specific molecular solutions are universal features of life or merely one evolutionary pathway among many. Life on another world might use completely different information storage molecules, different catalysts, different solvents. It might be so chemically alien that we would not recognize it as life at all. Venus is a potential test case. If life exists in those clouds, it evolved under conditions radically different from anything on Earth. The extreme acidity, the scarcity of water, the sulfur-rich chemistry, all of these would have shaped Venusian biology into something we have never seen. The AFN is designed to detect organic molecules that fluoresce, which includes the kinds of ring structures common in terrestrial biochemistry. But Venusian life might use different molecular architectures entirely. The probe's detection capabilities are necessarily anthropocentric, tuned to find life as we know it, rather than life as it might be. This limitation highlights a broader challenge in astrobiology. How do you search for something when you do not know what it looks like? On Earth, We define life through a constellation of properties: metabolism, reproduction, evolution, response to stimuli, maintenance of internal organization against entropic decay. But these properties are descriptions of terrestrial life, derived from observing organisms that share common ancestry. They might not apply to life that arose independently under different conditions. The phosphine detection, whatever its ultimate explanation, illustrates this challenge. Phosphine is a biosignature on Earth because terrestrial biology produces it under specific conditions, but we have no theoretical guarantee that extraterrestrial life would produce the same molecules. Venusian organisms, if they exist, might metabolize sulfur compounds in ways that produce different chemical signatures entirely. The AFN sidesteps this problem by looking for a broader category: organic molecules in general, rather than specific biosignatures. Carbon-based chemistry with ring structures fluoresces at predictable wavelengths, regardless of whether it is produced by life. If the probe detects such molecules, something is producing them, and that something demands explanation whether or not it turns out to be biological. This approach is necessarily conservative. It might miss genuinely alien life forms that use completely different chemistry, but it also reduces the risk of false positives from unknown abiotic processes. A fluorescence detection would mean organic chemistry is present. The question of whether that chemistry is biological would require follow-up investigation. The scientific method demands this kind of incremental approach. We cannot jump from no data to confirmed extraterrestrial life in a single step. We must first establish that interest in chemistry exists, then characterize that chemistry in detail, then eliminate non-biological explanations one by one. The Venus Life Finder is step one. The Morning Star program provides the subsequent steps. There is also the possibility of ambiguous results. Science rarely produces clean answers on the first attempt. The phosphine controversy itself demonstrates this. Years after the initial detection, researchers still debate whether the molecule is truly present and what its source might be. Complex questions generate complex data, and complex data requires careful interpretation. The Venus Life Finder might return results that are neither clearly positive nor clearly negative. The fluorescent signal might be present but weak, or present in some altitude bands but not others, or correlated with particle sizes in unexpected ways. The data might suggest organic chemistry without proving it, or rule out certain explanations without confirming others. In such cases, the follow-up missions become even more critical. Ambiguity demands resolution, and resolution requires better data. A weak fluorescence signal would justify a more sophisticated instrument on the next probe. Altitude-dependent variations would motivate a balloon mission capable of sampling multiple layers. Unexpected correlations would inspire new laboratory experiments to understand the underlying chemistry. This is how science actually works, not through single experiments that deliver definitive answers, but through iterative investigations that progressively narrow the range of possibilities. Each mission builds on the previous one. Each dataset constrains the hypotheses that remain viable. The process is slow, frustrating, and often disappointing, but it is the only reliable way to understand complex phenomena. The Venus Life Finder is the first iteration. Whatever it discovers, positive, negative, or ambiguous, will inform the second iteration, and the second will inform the third. Eventually, if we persist, we will have an answer. But persistence requires attention. It requires funding. It requires public interest and political will. And right now, almost nobody is paying attention to the mission that might initiate this entire process. This is a limitation, but it is also an opportunity. If the probe detects nothing, it tells us that familiar organic chemistry is absent, but says nothing about unfamiliar chemistry we are not equipped to see. If the probe detects something, it tells us that familiar organic chemistry exists in a place where it should not, raising questions that will occupy scientists for generations. Either outcome advances our understanding. Neither outcome closes the door. There is a deeper philosophical point embedded in this mission. For centuries, the question, "Are we alone?" has been a matter of speculation. Philosophers have argued about it. Theologians have pondered it. Scientists have theorized about it. But nobody could actually test it. The question remained beyond the reach of empirical investigation. That is no longer true. We now have the capability to send instruments to other worlds and collect data that bears directly on the question. The Venus Life Finder is not asking for belief or speculation. It is asking for measurement. This shift from philosophical question to empirical investigation represents one of the most profound transitions in human intellectual history. For the first time, we can actually investigate whether life exists beyond Earth, rather than merely wondering about it. The outcome matters less than the process. Whether or not Venus's clouds contain life, the fact that we can now ask the question scientifically, that we can design instruments, build spacecraft, collect data, and analyze results, marks a fundamental change in humanity's relationship with the cosmos. We are no longer passive observers looking up at an unknowable universe. We are active investigators, reaching out to touch other worlds and learn what they contain. The Venus Life Finder is a small mission, a tiny probe, a single instrument, 5 minutes of data. But it represents something much larger. The moment when the ancient question, "Are we alone?" became a research program rather than a thought experiment. I want to return to a question I raised at the beginning. Why is nobody paying attention? The Venus Life Finder mission is not a secret. There have been press releases. Sara Seager has given public lectures. Peter Beck has discussed it in interviews. The Planetary Society has published explanatory articles. Academic papers describing the AFN have been peer-reviewed and published. And yet, search news archives and you will find almost nothing. Ask random people on the street about upcoming space missions, and they might mention Artemis or Mars rovers, or perhaps SpaceX's Starship. Venus Life Finder does not register. Part of this is structural. NASA missions receive NASA publicity. Private missions have smaller megaphones. A $10 million project does not generate the press coverage of a $500 million project, even if the scientific questions are equally profound. Part of it is timing. The Phosphine controversy in 2200 generated enormous media attention, but the coverage focused on the controversy itself rather than on potential missions to resolve it. As scientific debates dragged on, public interest waned. The moment passed. Part of it is, frankly, our collective failure of imagination. Venus is not Mars. It does not have rovers named Curiosity or Perseverance with cute Twitter accounts and birthday celebrations. It does not have photographs of orange deserts that look like Arizona with a sepia filter. It has hellish surface images from Soviet probes 40 years ago and technical discussions of atmospheric chemistry that require graduate-level education. to fully understand. Venus does not make for easy storytelling. And so, Venus gets ignored. But the neglect of Venus also reflects something deeper about how we allocate attention in the modern world. We are drawn to narratives. Mars has rovers with names. Mars has red deserts that look like Arizona. Mars has a future colonization narrative that Elon Musk promotes on social media. Mars has science fiction stories stretching back over a century, from H.G. Wells to Ray Bradbury to The Martian. Venus has sulfuric acid and crushing pressure, and temperatures that melt lead. Venus is the planet where probes die screaming after 2 hours of operation. Venus is the cautionary tale about runaway climate change, the example we point to when we warn about the dangers of carbon emissions. Mars is aspirational. Venus is terrifying. This asymmetry shapes public perception far more than scientific merit. The questions we can ask about Venus are no less profound than the questions we ask about Mars. The probability of finding answers may actually be higher. Venus's clouds are active environments today, not fossil records of ancient times. But Mars fits neatly into human narrative conventions, and Venus does not. The Venus LifeFinder mission is an attempt to change this. If it succeeds, if it returns data suggesting organic chemistry in the clouds, Venus will suddenly become the most interesting planet in the solar system. The narrative will shift. The funding will follow. A generation of scientists will redirect their attention to a world that has been ignored for too long. And if it fails, if it returns null results, then at least we will have tried. At least we will have asked the question, instead of assuming we already knew the answer. There is something poetic about the timing of this mission. Venus LifeFinder launches almost exactly 60 years after Mariner 2 became the first spacecraft to successfully fly by another planet. And that planet was Venus. December 14, 1962. Humanity's first direct contact with another world. The data Mariner 2 returned shattered illusions about Venus as a potential habitable paradise, revealing instead a hellish world with temperatures far exceeding expectations. Now, 6 decades later, we return with a more nuanced question. Not, is Venus habitable? But might some region of Venus, against all odds, harbor conditions where something can survive? The question has evolved because our understanding has evolved. We know about extremophiles. We know about atmospheric chemistry. We know about the narrow altitude band where temperatures and pressures resemble Earth. The first Venus exploration taught us how hostile the surface was. This next chapter asks whether hostility extends all the way up or whether the sky offers refuge. This matters because we are living through an extraordinary moment in space exploration, and we are barely paying attention. The Venus LifeFinder is one component of a larger transformation. Rocket Lab is demonstrating that interplanetary missions no longer require billion-dollar budgets and decade-long timelines. Small teams with focused objectives can reach other worlds faster and cheaper than the traditional aerospace establishment ever imagined. This changes everything about how we explore. Instead of waiting 15 years between missions, we might launch probes every time a planetary alignment opens a launch window. Instead of designing instruments to answer every conceivable question, we might send specialized probes that each answer one question definitively. The accumulation of narrow answers might paradoxically give us broader understanding faster than the traditional approach. And if this model works for Venus, it works for everywhere else too. The moons of Jupiter, the methane lakes of Titan, the subsurface oceans of Europa. Small, cheap, focused missions could transform astrobiology from a speculative field with occasional data points into a rigorous science with continuous observation. The Venus Life Finder is a test case. If a handful of scientists working nights and weekends with philanthropic funding and borrowed hardware can send a probe to another planet to search for life, then the barriers we thought existed were never as solid as we believed. Consider what has happened in spaceflight over the past decade. SpaceX demonstrated that rockets can land and be reused, slashing launch costs by orders of magnitude. Companies like Planet Labs have deployed fleets of hundreds of small satellites, democratizing Earth observation. Blue Origin and Virgin Galactic have made suborbital spaceflight accessible to private citizens. Starlink has created a global internet constellation that would have been financially impossible 15 years ago. The economics of space have been fundamentally transformed. What once required national budgets now requires merely sufficient ambition and competent engineering. The gatekeepers, the national space agencies that controlled access to orbit and beyond, are no longer the only game in town. The Venus Life Finder is a product of this transformation. It exists because a small aerospace company, founded by a self-taught engineer from New Zealand, decided to challenge the assumption that interplanetary missions require billion-dollar budgets. It exists because a MacArthur-winning astrophysicist decided to organize a mission through Zoom calls and philanthropic fundraising rather than government grant applications. It exists because the tools and expertise that were once locked behind institutional barriers have become accessible to determined outsiders. This is not anarchic disruption. The mission still relies on rigorous engineering, peer-reviewed science, and decades of accumulated knowledge about interplanetary navigation and spacecraft design, but the organizational model is completely different from anything that came before. The implications extend beyond any single mission. If Venus Life Finder succeeds, not necessarily in detecting life, but simply in demonstrating that a small team can execute an interplanetary mission for a fraction of traditional costs, other small teams will follow. Missions to asteroids, to Martian moons, to outer planet satellites, all become more plausible when a $10 million Venus mission demonstrates the viability of the approach. The solar system opens up to exploration in ways that seemed impossible when only national space agencies could afford the ticket. Universities might send probes to study specific asteroids. Private foundations might fund missions to investigate questions too speculative for government programs. The iterative, rapid response approach of the Morningstar program might become a template for exploring other worlds. This is the real significance of the mission, independent of whatever it discovers about Venusian chemistry. It proves that the future of planetary exploration does not belong exclusively to NASA and ESA and JAXA. It belongs to anyone with the knowledge, the resources, and the determination to build a spacecraft and send it to another world. The democratization of space exploration is already underway. The Venus Life Finder is part of that story. A small chapter perhaps, but an important one. Now let me tell you what I think about. I think about that 5-minute window. I think about the probe falling through sulfuric acid clouds, with its laser firing thousands of times per second. I think about the fluorescence detector waiting for a specific wavelength of light that might never come. And I think about what it would mean if that light appears. For all of human history, we have been alone, not metaphorically, literally. We have never found unambiguous evidence that any other living thing exists anywhere in the universe beyond Earth. Every argument for extraterrestrial life has been statistical. The universe is so vast, surely we cannot be unique. Or theoretical, the chemistry of life seems straightforward. Surely it arises wherever conditions permit. Statistics and theory are not data. We remain, as far as empirical science can determine, the only life in an otherwise dead cosmos. The discovery of even simple microbes on Venus would shatter that isolation. It would prove that life is not a one-time accident, but a cosmic inevitability. If life arose independently on two planets in the same solar system, the implications for the rest of the universe become staggering. The galaxy would not be mostly empty. It would be teeming with life, most of it too distant to detect with current technology, but real nonetheless. That knowledge would change us, not the scientific establishment, but humanity itself. The cultural and philosophical implications of confirmed extraterrestrial life extend far beyond academic journals. We would know, finally and forever, that we are not alone. Let me be more specific about what this knowledge would change. The discovery of extraterrestrial life, even simple microbial life, would immediately become the most cited scientific finding in history. It would appear in every biology textbook, every astronomy course, every philosophical discussion of humanity's place in the universe. It would shape policy debates about space exploration funding for generations. It would influence religious thought, secular philosophy, and cultural production in ways we cannot fully anticipate. Consider how previous discoveries of cosmic significance have reshaped human understanding. Copernicus demonstrated that Earth is not the center of the universe, fundamentally challenging the medieval worldview. Darwin showed that humans evolved through natural processes, transforming biology and philosophy simultaneously. Einstein's relativity theories reshaped our understanding of space, time, and energy in ways that still influence technology and thought. A century later, the discovery of extraterrestrial life would stand alongside these moments. It would prove that life is not a cosmic accident confined to one planet, but a phenomenon that arises whenever conditions permit. It would suggest that the chemistry of biology is not unique to Earth, but follows universal patterns. It would make the existence of intelligent life elsewhere in the galaxy the subject of endless speculation, but no evidence, seem suddenly more plausible. And it would raise questions that we have never had to seriously consider. What ethical obligations do we have toward extraterrestrial life? How should we approach contact, if contact ever becomes possible? What rights, if any, do non-terrestrial organisms possess? How should the discovery be governed, shared, and studied? These questions currently seem abstract, hypothetical, the stuff of science fiction scenarios rather than serious policy discussions. The detection of Venusian life would make them urgent and concrete. Philosophers, ethicists, lawyers, and diplomats would suddenly have work to do that had previously been confined to academic speculation. The Venus Life Finder cannot answer all of these questions. A positive detection of fluorescence would not prove life exists. It would only suggest that organic chemistry is present in a place where it should not be. Years of follow-up investigation would be required to determine what that chemistry represents. But the detection would change the frame. It would shift the conversation from, is life possible elsewhere, to what kind of life exists elsewhere. That shift from possibility to investigation would transform astrobiology from a speculative science into an observational one. And that transformation would be irreversible. Once you know that life exists beyond Earth, you cannot unknow it. The cosmos becomes a different place, populated not just with stars and planets and nebulae, but with other living things that arose independently of terrestrial evolution. There is a counterpoint worth considering. The probe might find nothing. The clouds of Venus might be exactly what conventional chemistry predicts: sulfuric acid droplets with traces of photochemical byproducts suspended in a carbon dioxide atmosphere. Interesting to atmospheric scientists, but devoid of biology. The phosphine detections might be explained by volcanic activity we have not yet characterized, or photochemistry we have not yet modeled, or instrument errors we have not yet identified. A null result would be disappointing, but not devastating. It would constrain the possibilities, narrow the search space, and inform the design of future missions. Science progresses through negative results as well as positive ones. But I do not think a null result would close the door on Venusian life. The AFN can only detect organic molecules that fluoresce at specific wavelengths. It cannot detect life based on entirely different chemistry. It samples the atmosphere along a single descent trajectory through a single region of the clouds. Venus is an entire planet, complex, dynamic, and largely unexplored. One probe cannot answer the question definitively. What it can do is tell us whether to keep looking. The summer of 2026 approaches. In New Zealand, engineers are integrating hardware. In Hawaii, scientists have calibrated instruments on volcanic plumes. In laboratories around the world, researchers are training neural networks on simulated data to extract maximum information from the probe's limited bandwidth. Every day brings the mission closer to reality. Every technical milestone, successful vibration testing, communication system verification, thermal vacuum chamber qualification, reduces the uncertainty about whether the probe will survive its journey. The engineering challenges are formidable but finite. Solutions exist for every problem that has been identified. The launch window opens. The Neutron rocket rises from its pad, carrying a Photon spacecraft with a small cone-shaped probe attached. The spacecraft enters its cruise phase, coasting across the gulf between Earth and Venus. 128 days, 4 months, and a few days. The probe approaches the morning star. Separation. The Photon cruise stage fires thrusters to divert itself from the incoming trajectory. The probe continues alone, a 17-kilogram titanium vessel carrying a single instrument and the hopes of everyone who has worked to send it there. Entry. The heat shield glows. The probe decelerates from interplanetary velocity. G-forces building to 60 times Earth gravity. The titanium shell protects the electronics inside. The probe survives descent. The AFN powers up. The laser begins firing through its fused silica window. Cloud particles enter the beam and scatter light. The detectors record everything: polarization, intensity, wavelength, transmitting data to Earth at 125 bytes per second, 5 minutes, 330 seconds, the most important 5 minutes in the history of astrobiology, compressed into a plummeting capsule with a question older than civilization. Are we alone? The laser fires. The detectors watch. The data streams toward Earth. And somewhere in those signals, perhaps, is an answer. In New Zealand, engineers are integrating hardware. In Hawaii, scientists are calibrating instruments. In laboratories around the world, researchers are training neural networks on simulated data to extract maximum information from the probe's limited bandwidth. The launch window opens. The rocket rises from its pad on the Mahia Peninsula, carrying a spacecraft the size of a microwave oven toward a planet that no human has ever visited, that no robot has explored for nearly half a century, that might harbor answers to questions we have asked since we first looked up at the stars. 128 days later, the probe reaches Venus. It separates from its carrier spacecraft. It plunges into the atmosphere at speeds that generate heat approaching the surface of the sun. It survives. It decelerates. It falls through the clouds. The laser fires. The detectors watch. The data streams toward Earth at 125 bytes per second, crossing the gulf of space toward a species that has wondered, for all its history, whether anyone else is out there. 330 seconds. 5.5 minutes. The most important 5.5 minutes in the history of astrobiology, compressed into a plummeting titanium sphere with a single instrument asking a single question. Are we alone? And then, one way or another, we will have an answer. I want to end with something Carl Sagan wrote in 1994, near the end of his life, reflecting on a photograph called Pale Blue Dot, an image of Earth taken by the Voyager 1 spacecraft from 4 billion miles away, showing our entire world as a single pixel of light suspended in a sunbeam. Look again at that dot, he wrote. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. He continued, the Earth is a very small stage in a vast cosmic arena. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. Sagan was writing about humility in the face of cosmic scale, but there is another way to read those words. We are not merely a pale blue dot. We are a pale blue dot that has become aware of itself. We are matter that has organized itself into structures capable of asking what else might be out there. We are the universe looking back at itself, wondering. Sagan himself was intimately connected to the question of life on Venus. In 1961, he published a paper proposing that Venus might be terraformed using photosynthetic bacteria to convert its carbon dioxide atmosphere. In 1967, he co-authored the seminal paper with Harold Morowitz speculating about life in the Venusian clouds. Throughout his career, he returned to Venus again and again as an example of how a potentially habitable world could transform into something hostile, and of how that transformation might illuminate Earth's own future. The phosphine detection in 2020 would have fascinated him. Here was exactly the kind of anomalous observation that Sagan championed as the starting point for scientific investigation. Not proof of anything, but a puzzle demanding explanation. A mystery that could only be resolved by sending instruments to collect data. The Venus Life Finder embodies Sagan's approach to science. Follow the evidence, ask bold questions, design experiments that can actually distinguish between hypotheses. Do not assume you know the answer before you look. If Sagan were alive today, I suspect he would be championing this mission. He would be explaining to audiences why Venus matters, why the clouds might harbor life, why a small probe with a focused instrument could contribute to one of humanity's oldest questions. He would be doing exactly what this script is trying to do, getting people to pay attention. But Sagan is gone, and the task of paying attention falls to the rest of us. The Venus Life Finder will launch whether or not the public notices. The probe will fall through the clouds whether or not anyone outside the mission team is watching. The data will arrive whether or not the media covers it. But what happens next depends on attention. If the mission generates interest, funding follows. If funding follows, more missions launch. If more missions launch, we learn more. The iterative process of science requires support, and support requires people caring about outcomes. This is why telling this story matters, not to hype a mission beyond its actual capabilities. The Venus Life Finder might well return null results, and that would be scientifically valuable too. But to ensure that whatever happens, people notice, we are sending a probe to search for signs of life in the clouds of Venus. This is happening, this is real, and almost nobody knows about it. Consider that sentence for a moment. Consider what it says about human priorities, that a mission explicitly designed to search for extraterrestrial life, perhaps the most profound scientific question we can ask, is proceeding in near obscurity, while culture wars and celebrity gossip dominate attention. We could be watching history unfold. We could be following along as a tiny probe plunges into sulfuric acid clouds and fires lasers at particles that might contain the chemical signatures of life that arose independently of Earth. We should be watching. This is why we explore. This is why we build spacecraft and train engineers and fund science. This is why we look up. And now, for the first time in history, we have built the tools to go looking for an answer. That probe falling through Venus's clouds carries more than instruments. It carries the weight of every question humanity has ever asked about its place in the cosmos. It carries the hopes of scientists who have devoted their lives to understanding life's limits. It carries the dreams of a species that has always wondered in the darkness between stars whether the light of consciousness burns anywhere else. There is one more thing I want you to understand. The odds are against detection. Venus's clouds are probably exactly what conventional chemistry predicts: sulfuric acid droplets with traces of photochemical byproducts. The phosphine signal is probably a measurement error or an unknown abiotic process. Life in such an extreme environment is probably impossible, even for organisms we cannot imagine. Probably. But probably is not certainly, and impossible has a poor track record in the history of science. Things that seemed impossible, heavier than air flight, splitting the atom, observing exoplanet atmospheres, turned out to be merely difficult. The limits we assume turn out, again and again, to be the limits of our imagination rather than the limits of nature. The Venus Life Finder is a bet against probability, a small probe with a single instrument, asking a question that most scientists expect to answer negatively. The team knows this. They are not foolish dreamers expecting to find alien microbes. They are rigorous scientists designing an experiment that can distinguish between hypotheses and that might, just might, return data that no one expected. That might is why the mission matters. Not because success is likely, but because success is possible, and the implications of success would be so profound that even a small probability justifies the effort. The history of science is filled with long-shot experiments that transformed human understanding. Michelson and Morley's attempt to detect the luminiferous ether, which they expected to find, instead disproved its existence and set the stage for Einstein's relativity. The detection of the cosmic microwave background radiation was an accidental discovery during a communications experiment. The first exoplanet detection was considered so unlikely that the astronomers who found it spent years verifying their results before publishing. Transformative discoveries often come from experiments designed to test one hypothesis that end up confirming something entirely unexpected. The Venus Life Finder is designed to detect organic molecules, but who knows what else it might find. The clouds might contain chemistry we never anticipated. The particle distributions might reveal atmospheric dynamics we do not understand. Even a negative result, no fluorescence detected, would be scientifically valuable, constraining the range of possible atmospheric compositions. Science is not about confirming what we already believe. It is about testing what we think we know against what the universe actually does. Every experiment, every measurement, every mission that returns data contributes to this process, regardless of whether the results match predictions. The Venus Life Finder will contribute. Whether it detects life, detects organic chemistry without life, or detects nothing at all, it will add to humanity's understanding of our nearest planetary neighbor. And that understanding might eventually answer the question that motivated the mission in the first place. The Soviets sent metal spheres into Venus's atmosphere decades ago and captured grainy images of volcanic rock before the planet destroyed them. They were pioneers, explorers, seekers of knowledge against impossible odds. Now we go back, not with enormous government programs and billion-dollar budgets, but with a handful of dedicated scientists, a small aerospace company, and a probe that costs less than many houses. The Venus Life Finder mission is humanity at its best, curious, determined, reaching for answers that may forever change how we understand ourselves. Sometime in the summer of 2026, that probe will launch. 128 days later, it will arrive at Venus. 5 minutes after entering the clouds, it will fall silent. And in those 5 minutes, we might discover that we have never, in all our isolation, been truly alone. Let me bring this back to something tangible. Right now, as you read these words, the Venus Life Finder probe is being assembled. Engineers are testing the autofluorescence nephelometer, firing its laser thousands of times and measuring the scattered light. Scientists are refining the neural network algorithms that will compress the data for transmission. Mission planners are calculating the precise trajectory that will carry the spacecraft from Earth to Venus. This is not a concept. This is not a proposal. This is hardware being built, software being written, people working long hours to make an interplanetary mission happen. The probe will fly. The question is only what it will find. And somewhere in a laboratory, perhaps at MIT, perhaps at Georgia Tech, perhaps at Droplet Measurement Technologies, someone is looking at calibration data and wondering whether they are preparing an instrument that will make the most important discovery in the history of science. That person cannot know. Nobody can know until the probe enters the Venusian clouds and the data starts streaming back. But they go to work anyway. They refine the instrument anyway. They solve the engineering problems and run the simulations and prepare for a moment that might be transformative or might be anticlimactic. This is what exploration looks like. Not glamorous and certain, but grinding and hopeful. Not knowing in advance whether the effort will be worth it, but committing to the effort because the question is worth asking. The Venus Life Finder mission embodies this spirit. A small team, a limited budget, a narrow scientific objective, and the possibility, remote but real, of discovering something that would change everything. I began this narrative by asking why nobody is talking about this mission. I want to end by suggesting that this might be changing. The Phosphine controversy, whatever its ultimate resolution, reawakened interest in Venus among planetary scientists. NASA's selection of DAVINCI and Veritas, despite their delayed timelines, signals institutional commitment to Venusian exploration. The European Space Agency's Envision mission, also scheduled for the early 2030s, will add another orbital platform for studying the planet. India's space agency, ISRO, is developing its own Venus orbiter. China has proposed Venus missions for later in the decade. Russia has discussed reviving the Venera program, though funding remains uncertain. Japan's Akatsuki orbiter continues to study Venus's atmospheric dynamics. This international resurgence in Venus exploration represents something significant beyond the scientific questions involved. For decades, space exploration has been dominated by competition, the space race of the Cold War, the ongoing rivalry between NASA and Chinese space capabilities. But Venus exploration increasingly looks like a collaborative enterprise. NASA is contributing radar systems to ESA's Envision mission. Scientists from multiple nations collaborate on data analysis from existing missions. The Venus Life Finder itself involves researchers from institutions across the United States and internationally. The questions about Venus, whether life exists there, how the planet evolved, what its atmosphere can teach us about climate, transcend national boundaries. They are human questions asked by a species that evolved on one rocky planet and now wonders about conditions on another. This collaborative spirit extends to the relationship between government and private enterprise. The Venus Life Finder is a private mission, but it builds on decades of NASA and ESA technology development. Rocket Lab uses experience gained from government contracts to enable private interplanetary exploration. The boundary between public and private space activities has blurred in ways that benefit both sectors. If the 2030s truly become the decade of Venus, with DAVINCI, Veritas, Envision, and potentially multiple Morningstar missions all operating, we will see the most intensive exploration of any planet since the Mars campaigns of the 2000s and 2010s. We might finally answer questions that have lingered since the 1970s. What exactly are the clouds made of? Why does the unknown UV absorber exist? Is the phosphine signal real? And most importantly, is there anything alive up there? The Venus Life Finder is not operating in isolation. It is the leading edge of a broader return to our closest planetary neighbor, a return that has been delayed far too long, but is finally materializing. If the mission succeeds in generating public interest, if it captures attention the way Mars rovers have captured attention, it might accelerate this broader return. It might shift funding priorities and media coverage. It might make Venus interesting again in ways that go beyond scientific publications. And that, in some ways, would be as significant as any detection of organic chemistry, because exploration requires support, and support requires attention. The Venus Life Finder is asking humanity to look at a world we have ignored for too long and to consider the possibility that something extraordinary might be waiting there. Whether or not we find life, the asking is worthwhile. That is why this mission matters. That is why you should be paying attention. That is why when you look up at the evening sky and see Venus burning bright near the horizon, the morning star, the evening star, the planet that has captivated human imagination since we first developed the eyes to see it, you should remember that a small probe is on its way there with a question older than civilization and an answer that could change everything. We are going to Venus to find aliens, and nobody is talking about it. Not yet, but you are now. You have just spent the time to learn about a mission that most people will never hear about. You understand why Venus matters, why the clouds might harbor life, why a tiny probe with a single instrument represents something larger than its components suggest. When the launch happens, sometime in the summer of 2026, you can be among the people paying attention. When the data arrives 128 days later, you can be among those who understand what is at stake. When the results are analyzed in the weeks and months after the 5-minute descent, you can appreciate what they mean. Spread the word, tell people about the Venus Life Finder, explain why it matters. Share the story of Sara Seager and Peter Beck and the small team working nights and weekends to send a probe to another planet. Make this mission part of the public conversation it deserves to be. The search for extraterrestrial life is not an abstract scientific enterprise. It is a human endeavor, motivated by human curiosity, conducted by human beings who wonder about the same questions everyone wonders about. It deserves human attention. We are going to Venus. We are sending a probe into the clouds. We are looking for evidence that life exists beyond Earth. This is happening. Pay attention.